Recording, so let's go ahead and do this. So the 10.3, 10.4. Again, this is going to be completely review from last year, unless I think all the chemistry classes made it to gases last year, didn't they? Okay, so yeah. So and we're not even to Puvnert yet. No, actually we are. That's 10.4. Okay, so 10.3 is basically talking about the various gas laws, and then it talks about Avogadro's law, and then 10.4 you basically combine a bunch of those together, and you end up with Puvnert, okay? And then you also have they talk about the combined gas law in 10.4. So seriously, this is easy stuff. You guys are going to be fine on this. We talked about characteristics, we talked about pressure, we talked about conversions, standard pressure. Okay, so variables affecting gases. The typical ones that we talk about are pressure, volume, temperature, and how much gas do you have, okay? So PVT and N. So then actually it's funny because every once in a while this will happen. My chemistry class is doing gases right now as well. We kind of flipped the way that we're doing things, so we're doing gases earlier in the year. So it just turns out, I mean, it wasn't planned this way or anything, but it just turns out that you're covering gases at the exact same time as they are. So they crushed the cans today. Remember that?
Are we doing that?
Where you boil the water. No, we're not doing that this year. You did it last year. Sorry. Unless you missed it.
I was gone.
Oh, were you? That's funny.
I've seen it done, but I wasn't there for it.
Yeah. Okay, so Boyles Law is the relationship between pressure and volume. Okay? And actually, see, I have these set up, but one of the other chemistry teachers took them, so I can't even show it to you right now. You guys remember the Cartesian diver thing? Where I had a 2-liter bottle, and then I had a test tube turned upside down inside of it, and you squeeze it, and the test tube falls. I did it with a ketchup packet in here too. You guys remember that?
Well, it was mustard.
Mustard, that's right. Yeah, the mustard worked better. I just grabbed a bunch of condiments from Quick Trip that day.
Is that where you got all those ketchup packets?
Yeah. So anyway, point is, when you increase the pressure on a gas, it reduces its volume. Okay? I mean that makes common sense, right? So, and that's the thing with gases. Most gas stuff makes common sense. So you increase the pressure, you decrease the volume. You decrease the pressure, the volume of the gas increases. So they are inversely related to one another. They're inversely proportional. Okay? So then here's another way of looking at that. If you take this big box here and somehow you can shrink it down, then you have the volume that doubles the pressure. Okay? So pretty simple stuff. The plot of volume versus pressure is going to look like this, okay? And so since pressure times volume is equal to a constant, then you can rearrange that and you can say volume is equal to the constant over P, which means if you plot volume versus 1 over P, that's going to give you a straight line, if you cared.
I don't know how they
Okay.
figured that.
There's just people who sit in rooms all day and play with math.
Psychopath?
Maybe. I don't know. Okay. So, again, we can sort of, through some derivations, you can get P and V on the same side. P times V equals a constant. This is not a very hard derivation. If you've got P times V is equal to K, and then let's say that's your initial pressure and volume conditions, then you change 1, so now you changed your pressure, so now you're going to have a different volume, but they're still going to be equal to that constant K, all right? If they're both equal to K, then they're both equal to each other, and so you end up with P1 V1 equals P2 V2, all right? So that's Boyles Law, P1 V1 equals P2 V2. And you don't even have to memorize that. It's on your equation sheet. I am almost certain. You might check just to make sure. There's a gas section on your equation sheet. I want to make sure that I'm telling you the right thing. It used to be on the equation sheet. I think it still is. So then you've got these kinds of problems, right? So volume of 1 mole of ammonia gas at 1 atmosphere of pressure is gradually decreased from 78 to 39 milliliters. What's the final pressure if there's no change in temperature?
There is no P1.
Oh, is there not? Okay. So you got Puvner. Do you have the combined gas law, the P1 V1 over T1 equals P2 V2 over T2?
Holy what?
Oh, okay. Huh. Interesting. All right, so you just have PV equals nRT. Okay. Okay. Well, then I would say, in light of that, there's probably two things that you need to memorize as far as gas equations from the typical gas laws. No, one thing. Okay. And we'll get to that in a minute. And actually, in the books, this is interesting. It actually comes in more handy than I thought. There's a derivation on page 405 that helps you to get from Puvnert to this combined gas law right here. Okay. So really, all you need is Puvnert, and if you know how to derive it, then you can figure this one out. But I don't think you're going to have too much trouble remembering that, and that's not all that difficult. You just have to remember what's directly related to what's inversely related to what, okay? Because the pressure and volume are inversely related, they need to be on the same side at the top of the fraction, okay? If they're inversely related, if they're directly related, then they need to be on opposite sides of the fraction or opposite sides of the equation, one of the two, okay? So then all you're doing on that one is just a P1 V1 equals P2 V2 to solve for that problem. I mean, do we really need to go over that? I guess I will say this, as far as units are concerned. Once we get to Puvnert, you need to pay close attention to units, all right? When you're doing these gas laws, the only thing you need to be concerned with is that they have the same unit from one side to the other, okay? So in other words, if you use milliliters for your V1, then use milliliters for your V2. They need to match, okay? But nothing has to be in liters or, kilopascals or anything. It doesn't have to be in any particular pressure or any particular volume unit yet, okay? Once we get to PV equals nRT, it will. Okay? Just make sure that they're the same. All right, Charles' law is the next one. Volume of a gas is directly proportional to the Kelvin temperature. Okay, so an example of that, you have a 0-degree flask. You have a balloon that's deflated sitting on top of it. Put it into boiling water, and now it's, I guess, happy. Because if it was sad before, it's happy now. So the balloon actually is inflated a little bit because now the pressure has increased. All right? I'm sorry, the volume has increased. The pressure is going to be the same because the balloon is expanding to accommodate for that. So volume and temperature are directly proportional, so the way that you would end up writing that equation is like this, okay? Because you would have to say that volume is equal to a constant times the temperature. So then if you're solving for the constant, you end up with V over T is equal to K. And then if you have a V1 and a T1, you change the temperature. Now you've got a second volume, a second temperature, but they're still equal to K, so if they're both equal to K, then they're equal to each other. Not that you're ever going to have to derive these, okay, but just in case you're interested. All right, so that's Charles' law, and again, it's kind of showing the derivation / graph. So then there's a Charles temperature, or Charles equation. Now, this is one thing you do need to remember about the gas laws. Okay, I said the pressure and volume units don't matter right now as long as you keep them the same. The temperature units do matter. In every single gas law equation you ever do, it has to be in Kelvin, period. All right? Every single gas law problem has to be in Kelvin. And the reason for that is because Kelvin is the absolute temperature scale. All right? So we can only say what we say about volume and temperature being directly related if we're working with the absolute scale. And also, it just gets really awkward if you have a negative Celsius temperature and then you end up with a negative volume or a negative pressure at the end. So let's just stay away from that, okay? All right, so that's just the little bit about units there, but basically you're going to solve that problem using V1 over T1 equals V2 over T2. No problem. Avogadro's law basically just says that the volume is directly proportional to the amount of gas. Kind of a no-brainer, isn't it? If I blow up a balloon, it gets bigger. Okay? Avogadro came up with a law for that one, right? Got his name in the books because he came up with that law. So, oh, well, also because, yeah. But that's not, Avogadro didn't even come up with that number. It was named in honor of him later. So, anyway, so mathematically, basically the same thing as we talked about before. Now, here's something interesting, okay? If the volume is equal to a constant times the number of moles, then remember how our chemical equations, the coefficients tell us a mole ratio? You might remember this from last year if you were in my class. These coefficients also tell you a volume ratio. You remember that? When we're only working with gases and when everything else is constant, okay, if the pressure and the temperature are both constant, then this tells us if we have 2 volumes of hydrogen, in other words, 2 liters of hydrogen, plus 1 liter of oxygen, that's going to give us 2 liters of water vapor, okay? Only works if they're all gases, okay, but you can actually look at the coefficients in the equation and it will tell you a volume ratio as well as a mole ratio. And that's kind of useful to remember every once in a while because there are certain problems they might give you where you get a little bit stuck unless you know that, okay? All right, so sample problem, we've got a gas confined to a piston. Consider the following changes and indicate whether each will... Okay, we can talk about this one because it's just conceptual here. So there's actually no question here. Oh, there we go. A, heat the gas from 298 K to 360 while maintaining the present position of the piston. Okay? So in other words, we're not changing the volume, but we're heating the gas. So what is that going to do? That's going to increase the pressure. Is it going to do anything else? That's pretty much it, right? It's going to increase the pressure. I don't think it's going to do any of those other things because it can't decrease or increase the average distance between the molecules, and we're not adding any new gas into the cylinder. So, what about if we move the piston to reduce the volume of gas from 1 liter to 0.5 liters? So we're reducing the volume. What does that do? That increases the pressure as well, okay? Does it do anything else? That would also decrease the average distance between the molecules, okay? If we inject additional gas through the gas inlet valve, okay, it's going to decrease the average distance between molecules. It's going to increase the pressure of the gas. It's going to increase the total mass. And it's going to increase the number of moles. It does all of them, okay, if we put extra gas in. All right, so just a little...
I'm really liking this section.
Yeah, it's really not bad. The combined gas law is the T1 V1 over T1 equals P2 V2 over T2. So I don't know that we really need to say anything else about that other than just remember your temperature needs to be in Kelvin. Okay. And the ideal gas equation, I'm not real worried about the derivation here on this one, but basically we know that the volume is inversely proportional to the pressure. Okay. And the volume is directly proportional to the temperature, and it's directly proportional to the amount of gas. All right. So the way that we would write that is like this bottom equation down here. Okay, the volume is directly proportional to the N and the T. It's inversely proportional to the P. So then you rearrange that a little bit. And, oh, well, the other thing you have to think about here, they're proportional. That doesn't mean equal, right? How do you change a proportionality to an equality? You need a constant, right? Okay, so in this case, the constant is important enough it gets its own name. It's called the gas constant R. Okay? And here are some of the units. Now, they give you several units for R, don't they, on your equation sheet? You guys put them away already, sorry. What time is it? Let me make sure we get done. I think we're going to.
Go quick, Dr. J.
I'm trying. Okay, 4 minutes. It does give you several. Or does it just give you... Okay, yeah, I would assume it gives you the liters times atmospheres over mole times Kelvin, the joule over mole times Kelvin, and then does it give you the torr?
Yep.
Okay, so these three right here, the top two and the bottom one are the values for R that they're going to give you on the AP exam, all right? So you don't have to remember that, you just need to know how to use it. And notice, the thing that's different on these R's is the unit of pressure, okay? Although this one's different. You're going to use this R in different scenarios. Probably the two that you're going to use for the gas laws are going to be the top and the bottom, okay? But the atmospheres versus the torr thing, that's the only thing that's different about these, so it just depends on which pressure unit you're using in your problem as to which R you're going to use, okay? So PV equals nRT, there it is, Puvner. The most famous gas equation in chemistry. So then STP, you need to know that that's 1 atmosphere and 0 degrees Celsius, but we don't use 0 in any of our problems, do we? Our gas law problems. We're going to use 273 Kelvin, okay? So, I don't know why that was funny.
No, I'm not letting it.
Oh, okay, all right.
I just, like, walked around the court, like,
Yeah,
whoa.
yeah, of course. So at STP, remember, 1 mole of gas is equal to 22.4 liters. You guys remember that from last year? No? Yeah, at STP, 1 mole of gas is equal to 22.4 liters, okay? We actually did a lab on that last year. You had a graduated cylinder turned upside down. You did magnesium and hydrochloric acid, and it bubbled up. Remember you had it in a cage? Copper cage? No one's remembering this?
I was gone.
Yeah, okay, there you go. Anyway, yeah, so you had a copper cage, and then you calculated the value for R. I don't think it really worked out for anybody. Or no, you calculated the 20, you were supposed to get the 22.4 number, but I think we were all fairly off on that one. Okay, so then, these are the kinds of questions you're going to get there. Now, with the ideal gas equation, you do need to watch your units. Your volume has to be in liters because of the R, okay? And your pressure, you just need to get it either into atmospheres or into torr, okay? Are probably the two that you're going to want to change it into to make sure that it fits with your R, okay? Other than that, I don't know that there's a lot we need to talk about with the... We've got some gas stoichiometry stuff to talk about, but that's in a different unit or a different section. We'll talk about that in 10.5 and 10.6. We'll talk about some of the gas stoichiometry stuff. So that's basically it. No problems there, right? Okay.
Everybody gets extra credit.
Yeah.